recently coming out where people want to do this log analytics, where people want to execute many more sophisticated queries like regular expressions. And that's also one of the interactive queries that I'm going to scope in. And the third set of queries, all these rise of social media and some of the systems that support very interesting queries over graphs. So for example, Facebook graph search, Twitter is also a search system, LinkedIn also supports search of some form. So, so basically on the right, I've listed some set of queries that I'm going to talk about or at least care about in this interactive query scope. Okay, and then there are other systems that want to do some other queries as well, like aggregate queries. But I'm going to focus mostly on the first 5, 6 set of queries. So that's what I'm going to call interactive queries in this talk. Okay, so how do people do these interactive queries today? So details vary across the system, okay, but there are two main techniques to execute these interactive queries today. The first one, so let's suppose I'm going to take this file where I have color encoded the characters. Now these can be characters, terms, or substrings in the file. And suppose I want to search for this green characters in the file. So first technique, which is also used in a Spark, at least used to be used in a Spark, is so-called data scans, right? So you would have your RDD of all these documents, and what you want to do is you store this input in your memory, and then you start, when a query comes in, you start scanning the file, okay? So it's not just the animation, data scans are actually that slow. So you have to scan the entire RDD for each query, right? So it gets slow. But the nice thing is that you have to store only the input file. So your storage overhead is actually very low. Okay, since you're storing only the input file, your storage overhead is low. On the other hand, your query latency goes very high as the file size increases as well. On the other hand, the database people have for many, many years developed this other techniques that is so-called indexes. Now this is a huge space and people have developed all kind of indexes. I'm going to present only a very high level overview of the trade-offs. So what people do is you store the input file because you still want to do random access, and in addition you pre-process the file and you store some pre-computed results. And here I'm showing a very simple case where I'm storing the inverted index for each of the characters where exactly the results or the offsets into the file where those characters are stored. So what's the nice thing about it? The nice thing is when a query comes in, you simply go to the index and you get your answer. Okay, so it's super duper fast. What's the problem? The problem is that you have to store this index in addition to your input file, so your storage overhead goes high, right? So basically I'm going to call it high storage and low latency. And we wanted to really understand that if we are actually stuck with one of these techniques, even when we wanted to speed up interactive queries on a Spark, or can we do something interesting beyond this technique? So right now, the way I presented data scans and indexes, there's a strong trade-off between storage and latency. This trade-off actually slightly gets stronger if you think about how the data scales. So let me try to give you that idea. So what happens at scale? And this is only qualitative. The numbers, exact precise numbers don't matter. Suppose I have on the x-axis the input size. On the y-axis, I want to understand what the latency looks like. So when the input size increases, data scans have performance something like this, which means when the scans can be in faster storage, you have certain latency that increases with the input file size. And once you go to slower storage, then your latency again keeps increasing, but there is a different trade-off curve, different slope. With indexes, they're super fast when they can be stored in memory, but unfortunately because of the high storage overhead, they run out of memory faster and you pay this cost of going to the slower storage. So this basically you are paying the cost of going to the slower storage with indexes. Okay. The question is whether we can do something at scale, which is when the input size increases, our performance doesn't go as bad as these two techniques, right? So that's where Succinct started. What we do in Succinct is we designed this distributed data store, and now it runs on top of Spark. It's an entirely compressed data store, okay? And it allows you to do these point queries, and I've listed some of the point queries that Succinct supports. For example, you can do search, you can do regular expressions, you can do even random access. And the interesting part is that Succinct doesn't require any indexes. Without even requiring indexes, it still avoids data scans, and all the queries are executed directly on the compressed form. so you don't have to decompress the data. Okay? So we are going to break that trade-off that I showed you earlier. So you don't store any indexes, you don't have to do scans, and all the queries are executed directly on the compressed form. Okay? And from the system side, we did another interesting thing. What Succinct allows you to do is we have this very simple unified interface that allows you to treat your unstructured data, key value stores, document stores, tables, all using a single unified format. Okay, so I'm going to talk a little bit about it as well, that how using a single interface you can think about your data as unstructured data or as tables or as key value stores or documents. So these are the two main things that I want to talk about today. So let me start with point queries. So like I said, Succinct takes your input file and it compresses it down to a small suite of data structures. The important thing here is, again, you don't store your input file. You are only storing these compressed suite of data structures, okay, which is a compressed representation of your input file. Now, once you have stored these files, you can execute all these powerful queries directly on this compressed representation. Okay, so what I want to convince you today is that you can achieve low storage and low latency. Okay, so we have taken that trade-off between scans, which was low storage, high latency, and indexes, which was high storage and low latency. I want to convince you that we have some interesting things where we can break that trade-off in some scenarios. So what makes Succinct really interesting is that you don't store any indexes, so you save a lot of space cost, or you can push more data in memory and execute a larger fraction of queries in memory. On the other hand, since we are avoiding data scans, we are essentially providing you the functionality of indexes. Okay? And finally, since we don't have to do data decompression, we don't have that overhead of decompressing the data with traditional compression techniques. So if I were to take this curve back and put Succinct there, what happens is Succinct goes all the way down to larger data sizes because you can push much more data in memory. At some point, Succinct will run out of memory and its performance will be slightly worse than indexes. Okay? But the gains that you get are precisely for this range where you can push an order of magnitude larger data sizes in memory, and you get those gains by avoiding data scans or by avoiding going to the slower storage. Okay? Are we on the same page until here? Okay, good. So let me now describe what Succinct can do and slightly deeper. So what Succinct does is it takes your input as a flat unstructured file. Okay, internally Succinct works with flat files, and I'll try to give you some idea about why this is such a powerful interface. So the input internally Succinct works with flat unstructured files. And on the left, I'm going to show you the original input and how the queries work on that input. On the right, I have Succinct. So what can you do with Succinct? You can search, right? That's so basically think of it as Elasticsearch or indexes functionality provided by a search. So once you search on Succinct, all the queries are being executed on the compressed data, but results are shown on the left side. So essentially, you are going to get the search results on the uncompressed file. The second query is you can extract, so you can do random access on this file, starting at any arbitrary offset, you can extract as many bytes as you need. So think of it as a key value pairs, right? The third thing is you can count, and the counts are super duper fast, and we have used these fast counts in Succinct to do a lot of optimizations of Spark SQL underneath. Finally, you can append new data, just like a Spark. You can add new data, and you can do range queries, and I'll talk a little bit about regular expressions later on. So you can actually do range. Actually, one nice thing about range queries in Succinct is that range queries have the same complexity as search queries, so your range queries are also just as fast as search queries. So we don't need data scans, we don't need secondary indexes, and we don't need data decompression. It becomes a very interesting question to understand what do we actually lose, right? This systems work, so you have to lose something if you want to gain something. So Succinct does make some interesting trade-offs, and I want to quickly outline what are the trade-offs. First of all, Succinct has to spend some time pre-processing the data, which means if you have a workload where you're going to execute a lot of queries after a certain time, then Succinct becomes interesting for you because you will save the time. If you have to run only 5 or 6 queries, then that pre-processing time becomes a high overhead. Second thing is when you are doing random access, Succinct requires extra CPU cycles because you have to decompress the data at least for that range of data that you're accessing. Succinct is primarily designed to enable random access into RDDs, which means that your sequential scan throughput is going to be lower. Okay, so this is not meant for long-running jobs where you have to extract the entire file, and I highly recommend you not to use Succinct to extract the entire file. And finally, Succinct does not support in-place updates. We support in-place updates, but by appends. So in-place updates is a tricky thing. Like I said, these things are supported, but just traded off in favor of random access or point queries and compressed data. Okay, so let me get to the other part, which is, I think, a super interesting side as well. What Succinct allows you to do is use Spark now as a collection of different systems. The first one is you can now analyze, yes?
If you don't do indexing, how do you do research and count?
So the way Succinct works is the indexed representation is embedded within the compressed representation. So you can think of it as...
It's basically back to structures.
Yes.
The original one and so you do indexing.
It's not a secondary index. So there's one single data structure that allows you to get the power of indexes plus the input data.
But it's still indexed that added that kind of back.
Sure, yes.
In addition to
yes.
the original set. So you have
No, that's what I want to point out, that it's not in addition to. It's one single data structure that is a compressed representation of your input, and the indexing information is embedded within this data structure.
Is it embedded or just added in the end of that structure?
It's embedded. So you don't store two different data structures. Okay. So there are no secondary indexes.
So you recalculate some kind of statistics, that's why they...
Absolutely, yes. Yes. That's why pre-computation time comes, yes. Okay. So you can use this unified interface to to use the Spark to work with unstructured data. You can also use the Spark now for some functionalities on key value stores like Dynamo or Voldemort. You can also use Spark now as a document store where you have a large set of documents like Elasticsearch and MongoDB. And you can also use Spark as doing these interactive queries on tables. Okay, and some more that I'll talk about towards the end. But the interesting thing is not only you are using Spark for all these functionalities, you're also getting very powerful queries on the tables or on the key value stores and document stores. Okay. Okay, so this is so I want to give you a very quick idea about this unified interface thing, how it works, because it's really simple. So here's what it does. So this is the Succinct interface or Succinct Spark interface. You submit your file as you want, like a table or a key value store or as a document store. So you submit a file as a collection of documents or tables. Okay. So here I'm showing just a table which has 4 columns. Succinct takes that file and internally assigns each column or each document a delimiter, okay? Not each document, but each document ending. So each column a delimiter, okay? I'll go slow a little bit. And then what it does, it transforms this table along with its delimiters into a flat file. How it does that, take the first column, it has a circular delimiter. It writes down this flat file with each value in that column appended with its delimiter, okay? So now we have a flat file. And then it constructs succinct data structures on top of that. So now imagine that a search query comes in which says, find me all the green blocks, but I only want the green blocks in the first column, right? Internally, again, this is a search query from the user side, so you don't see any changes or what Succinct is doing internally. You don't have to be bothered about that. Search query comes in. What Succinct does is internally transforms that search query to the following query. It takes that search query, which is green block, and just appends a delimiter. And now this green block appended by the delimiter executed on the flat file, right? And it's easy to see that you will only get the right results. You will only get the results in the first column, right? So now since I've shown you for tables, I can do it for key value stores, which is just 2 columns. I can do it for document stores and all the flat files and everything, okay? So using this very simple transformation, Succinct allows you to do these many different powerful models using a very simple interface. In fact, if you have a new data type, you can write a very simple serializer interface, write just this one where you will assign delimiters and you will change the queries and you are off to go, okay? Okay, great. So this is all I wanted to say about what Succinct can do. Now let me quickly go through where are we and how much time do I have? Oh, okay, perfect. So where are we and where are we going? Okay, so let me start with where are we. So we designed Succinct. Succinct is designed in two ways right now. The first one is as a standalone system, and we have prototyped this system, and we are testing, doing a lot of testing. We are also releasing it as a library, so if you have a version where you want to integrate it with one of your running systems, you can use it as a library. And it's written in all the interesting languages that you can think of. And this is primarily for ease of integration. Okay? So if you have a system that you want to start playing with Succinct, you can integrate Succinct using this as a library. And all the functionalities that I talked about are already supported. The other one, which is Succinct Spark, we have released Succinct Spark as a package that allows you to do queries on compressed RDDs, right? And I'll talk a little more about it. It's not that Succinct just allows you to do these search queries on Spark. It also allows to use a Spark in many new ways. For example, like I said, you can use a Spark as a document store now, and we have now Succinct Spark going into production cluster with Elsevier apparently, where they are actually using Succinct Spark as a document store. And you can execute these point queries on these document stores. You can also use Succinct Spark to implement faster filters. If you're implementing nice filters today, filters are implemented via scans in Spark, so you can get really fast filters. And since the RDDs are compressed, you can just use Succinct Spark as pushing more data in memory. Okay. I must note that data frames API is not so mature yet, but we are very actively working on that, so stay tuned. Okay, so I want to say a little more about Succinct Spark. When is it interesting? I talked about systems like Elasticsearch, right? There are two cases where Elasticsearch is interesting. One is where you want really high throughput. The other one is where you want really low latency. So if you're already using Spark, then Succinct Spark allows you to do these new functionalities without scans and do very powerful functionalities. The second one is you can do faster operations into RDDs, like I said, and you can do more in memory. But as of now, the current release of Succinct Spark is meant for low latency rather than very high throughput. But we are working on how to get a high throughput side of the Spark as well. But right now, you want to use Succinct Spark as a very low latency system for these queries. So let me quickly tell you some of the interesting APIs in Succinct Spark. So the first one is we have this new RDD, which is called Succinct RDD. It's very simple. You export some library, you import some classes, and then you create an RDD just like you do today with your favorite data type. And then we have this new operation that allows you to succinctize this RDD. Okay, so you can do .succinct, and now it is a compressed representation. Now this takes a little while. Okay, so this is where the pre-processing picture comes into picture. Once you have compressed this, now you have a new RDD which is called Succinct RDD. You can execute these powerful queries. So you can just do .search and search for all the records or all the key value pairs or all the documents that contain Berkeley. Actually, the Succinct RDD is only for unstructured data. And you can, as I said, you can also extract, you can do random access, and you can count. Okay. So this was Succinct RDD. Now if you wanted to deal with more semi-structured data, we have the Succinct KV RDD. Okay. That allows you to use it as a Spark as a document store. It's exactly the same. You do import classes, you create your data, you load your data, and you compress using Succinct RDD. The only thing is that I've changed the name to Succinct KV RDD now. Okay. Once you have the Succinct KV RDD, nothing changes. All the operations are the same. You do .search. The only change is in what you get. Right? If you're using it as a document store, what you get is the document ID rather than the offsets in unstructured data. Similarly, you can do a get now, which means you can extract the document, and you can do within a document you can also extract. For example, if you have Wikipedia articles which are large, you only want to extract certain bytes around your search results, you can also do random access into the document and not just get the entire document. So I want to show you some quick numbers. These particular results that I'm going to show you are with 5 EC2 servers, each with 30 gigabyte RAM. We are using a lot of RAM because we want other systems to fit in memory as well. And I'm going to use this Wikipedia dataset with 40 gigabytes. And I'm going to compare against Spark and Elasticsearch, okay? And for search queries with certain number of occurrences. Okay, so let's see what do search latency look like. So the x-axis here is the query latency, but it's at the log scale, okay? So you have to enlarge it to understand the numbers. So if I run Spark today for this particular search query that we had, I should have said this is in milliseconds, okay? So Spark takes around 10,000 milliseconds today to run this particular Spark query. Elasticsearch, which is outside of a Spark system, can execute this query in around 200 milliseconds. Okay? So it's around 5x faster than a Spark. And if you use Succinct Spark now, so Succinct integrated with Spark, you can execute this query in almost, almost 70 milliseconds, which means that you're roughly 2.75x faster than even Elasticsearch outside of Spark. And this is when everything fits in memory, so you are also being more space efficient because of succinct compression. Okay? So we are not being just space efficient, you can actually run faster queries with lower memory footprint, so you gain two advantages. So this was for search. And now I want to go into this very interesting direction that we have seen a lot of applications about. So Succinct Spark now, today you can download the package and run regular expressions on that. It supports regular expression queries. And the only thing that changes is in the two APIs that I showed earlier, you just replace search by regex search. Okay, that's the only thing that changes. And you can execute very powerful regular expression queries. For example, here I'm trying to find all matches where there can be anything between William and Clinton. Okay. Same thing in KV RDD, you can just replace search by regex search. Okay. Okay, so let me show you some numbers on regex search. I have exactly the same systems, except for that I've added Succinct out of Spark, just to show you something about Spark. And on the log scale, again, the query time is in milliseconds, but now, since it's regular expressions, some systems take a lot of time. So this goes all the way to 100,000 milliseconds. So this is what Spark looks like, extremely, extremely slow. Okay, if you want to run a regular expression. And the problem is that you are not just scanning the data, you also have to do some computations for executing regular expressions. If you run Elasticsearch, it's still almost 7x faster than Spark. Okay, so Elasticsearch is pretty good. Now, if I run the same query on Succinct Spark, I'm somewhere here, which is here I see much more benefits of Succinct Spark, not just 2.75x faster like search, but I'm actually around 5x, 6x faster. And finally, if you were to use a Succinct library or Succinct system, this is what you get. Okay, we are all almost 2 orders of magnitude faster than Spark. And this is the problem right now with the Spark as well, because there's just too much overhead of executing each query. Okay, and because of the job startup time. And this is what Succinct C++ code avoids, and you get really, really good benefits. Okay. So this is basically the regular expression. This is all and this is one particular query. Okay, regular expressions are really hard to characterize, but we are doing a lot more benchmarking here. But this is just some numbers. Okay, so we get really good, fast regular expression queries. Succinct Spark now also supports JSON documents, so you can actually work with JSONs very efficiently. And the only thing that changes is rather than using a Succinct KV RDD, you use a JSON RDD, and you can execute the same kind of operations on JSONs. And you can even do more complicated filters on JSON documents. Okay. Okay, great. So finally, what I want to talk about is where are we going? What are we doing right now? So one thing is more testing, more benchmarking. We really need your help with regular expression queries. That is one thing that we are loose with. We want real world regular expression queries that people are using. And if you have some nice data sets for us, we'll be very happy to do some more benchmarking on regular expressions. We're doing a lot more work on data frames. And I think that that API is going to get very interesting as well. And finally, we have some new functionalities that we are implementing right now on top of Succinct Spark. And let me give you some ideas about what we are doing with Succinct Spark new functionalities. So first thing I want to talk about is this very recent project that I'm a super big fan of. It's called Blowfish right now. And here's what it does. So I showed you this curve about query latency, and on the x-axis you can't see, it's just storage. Okay? So indexes were somewhere here, which means you had very high storage but very low latency. And Succinct was somewhere here, okay? Which means you had slightly higher latency than indexes, but you had very low storage. What this project Blowfish does is it allows you to choose any point on this trade-off space, okay? Which means if you had a data set of any size, you can choose what is the right amount of storage you need to fit the data in memory, okay? And not only that, if this is looking forward. You think about 2 years down the line, as the memory technology changes, or this 3D cross-point technology comes in, the trade-offs are going to change. Right? Right now, SSDs are 200x slower than memory. If you go to 3D cross-point, then it might be just 4x slower. So this project really allows you to look forward into the technology trends and say that, okay, if things change, you have a new operating point to choose along a trade-off curve. Okay? So the system is not just a fixed point solution. It allows you to choose the things as the technology evolves. Okay, so this is a super interesting project, and not just that, we have shown that using this Blowfish, this flexible trade-off curve, you can do many, many interesting things in terms of how to handle load spikes on your system, how to do error control, a lot of interesting things. So this paper was recently accepted. If you're interested, it's on Succinct website. It's one of my favorite projects. The second thing that we are doing is so-called succinct encryption, where what we are trying to do is not just queries on compressed data, but we are putting in encryption as well into the system, which means this project should, in theory, allow you to do queries on compressed and encrypted data. So you can get all the benefits of compressed data stores, but also get security of your data. This turns out to be a slightly more complicated project, and it's a very active project in the lab, and we are doing a lot more research in this direction. Finally, another very exciting project is Succinct Graphs, where we are trying to do queries on compressed graphs. And one of the interesting directions there is we have already built a Facebook graph store-like engine completely running on top of Spark. Okay, so you can do very, very interesting queries on graphs. For example, you can say, okay, tell me all my friends who live in Berkeley and who like this restaurant and who are also common friends with Jan Stoika. Okay, and you can execute these queries super duper fast directly on top of Succinct Spark today. This is not released, so you probably can't do it. So these are the three projects I wanted to talk about in terms of future work or ongoing work, and there are a lot more projects. So if you are excited about it, please talk to me. And if you have any suggestions or feedback, that's why we are here. So I'll be very happy to hear from you. I think I'm running out of time almost, but yes, thanks all for coming.
Excellent. So we're going to have time for about 2 questions now. So I saw your hand up first here.
I have a question about your C++ version. Okay. Was that a distributed solution, or was that just a single server?
It's a purely distributed solution. You can run it on CPU today on hundreds of machines. The interesting part there is, okay, I'm boasting, but the interesting part is that we took a 256 gigabyte RAM machine and we were able to execute sub-millisecond queries on half a terabyte of RAM on a single EC2 server with a C++ code. So you really want to, if that is something, C++ is something that you are happy with, you should definitely try out that system.
How did you distribute the C++ in library? If it's a library, how is it distributed?
No, so system is separate from a library. We have a system.
He asked about the library, right? You asked about the library.
I was just more interested in the C++ code.
Right, C++. I mean, in order to be distributed, you need the servers. I mean, he's talking about the library. It's not distributed in that sense.
Okay, let me say what I meant. So we have a system that we are running with, which is a C++, which is in C++, and we are also releasing a library for people to use that they can integrate with their current systems. Okay, so we have.
Are you talking about C++ library or servers?
We have both the library that we have released that you can integrate it with your systems, plus we have a standalone system that we are prototyping right now that you can start using already.
Okay. One more question.
So if our data is primarily numerical, like doubles, would this help?
So
how would you organize the data? Yeah.
Right, interesting question. So if your data is more numerical, you can still do range queries and search queries. The way we do it is, and I'll tell you what we lose there. The way we do it is we pad the integer digits such that every integer or double or float will have the same precision. And so lexicographic ordering is same as the integer ordering then. The trade-off there is that you might lose out on the compression factor a little bit because you're padding extra digits in the input data. But right now, that's the trade-off we are making. But yes, you can use this with the integer data as well, or floats or doubles.
Excellent. That's all the time we have for questions. So
Okay,
let's
perfect.
give
Thank you.
Dr. Agarwal a big round of applause.